Today I will be examining a scene from Indiana Jones and the Kingdom of the Crystal Skull. In this scene, Indiana Jones finds himself in a nuclear bomb testing area. A countdown begins till the bomb will detonate and Indiana Jones decides to hide in a lead-lined fridge. The bomb explodes and there is a blast followed by a shockwave. The fridge and Indiana Jones can be seen flying over a car traveling at full speed to escape the explosion. The fridge hits the ground and bounces several times before coming to a complete stop. So here we have our fridge with our balanced normal force and force of gravity. Therefore, the fridge is at rest. According to Newton's first law, objects continue in a state of rest or uniform motion until an unbalanced force acts upon it, which in this case is the force applied from the shock wave. Newton's second law states that force equals mass times acceleration, and we know that if mass increases, acceleration decreases because they are inversely proportional. This is where lead comes into play because it's dense and therefore heavy. So if you have the same force applied, but an increase in mass, there will be less acceleration. According to Newton's third law, for every action there's an equal and opposite reaction force. Therefore, when the fridge hits the ground and applies a force into the ground applies the same force onto the fridge. We will be solving for the maximum horizontal speed. In the 1950s, the average speed of a car was 44.704 meters per second, and the average length of a car was 3 meters. And we know in the movie the fridge traveled over the car in 0.97 seconds. So using velocity, delta d over delta t, we can solve for the instantaneous speed of the fridge traveling over the car and add it to the speed that the car was traveling at, and that will solve for the maximum horizontal speed of the fridge. So we are going to solve for the impulse using the horizontal velocity, 47.80 meters per second, which was previously solved for in the other question. So impulse equals to the change in momentum, and momentum is mass times velocity. So therefore, we're solving for the change in momentum, which is impulse, and the change in momentum is mass times the change in velocity. So the mass of the fridge is 143 kilograms plus Indiana Jones, 97.5 kilograms, is going to equal a total of 240.5 kilograms. Now we're going to multiply that times the velocity, which is 47.80 meters per second, and we are going to get the change in momentum and the impulse of the system, which is 11,495.9 kilograms meters per second. So now we plan to solve for the force, but first we're going to solve for the time. So we're going to use our impulse solved for previously, and we are going to find time, which is delta d over v. So we're going to use the speed of the wind, which is 277 meters per second, and this is found in the Hiroshima and Nagasaki nuclear bombs in Japan during World War II. So we know that the length or width of a fridge is 0.9 meters, so we're going to do 0.9 meters over 277 meters per second to get 3.25 times 10 to the power of negative 3 seconds. So now we're going to solve for our force using the impulse equation, force times delta t, and we're going to rearrange that. So force equals to impulse over delta t. So we'll use our impulse from before, 11,495.9 kilograms meters per second, over time, 3.25 times 10 to the power of negative 3 seconds, and we're going to get 3,537,200 newtons.